Awesome.
So today is Rocket Day, no surprise. So campers will be building and experimenting with different types of rockets, learning about how different rockets perform, understanding the effects of thrust and drag, and demonstrating Newton's third law of motion. For every action, there is an equal and opposite reaction. So I'm sure the campers have all sorts of questions that will help them with their rocket challenges. But first, as I mentioned, Dr. Schoellig, could you tell us a bit more about what you do in aerospace studies? And maybe specifically, you could start with what is aerospace studies?
Yeah. Okay. So I'm in aerospace studies, but I have to say that's not absolutely my background. So my background is controls and robotics, and here in aerospace we use it to enable or build space robots like the robot you see on Mars, but also to enable airplanes to fly on their own without any human input. So basically my research is to enable machines to do things on their own, like to fly on their own, to drive on their own, and that fits into aerospace studies where we study airplanes, rockets, robotics for space shuttles, and these kind of systems.
Excellent. Thank you. So let's get right to our first question. Is there a question in Ingersoll?
You have to speak louder. I didn't hear.
Yeah. Perhaps could you... We couldn't hear you. Maybe if you come right up to your iPad mic, it will help us hear you.
How much fuel does a rocket use?
How much fuel a rocket will use? To be honest, really, I'm not a rocket expert, to be honest. So I can only guess like you do, but I haven't built any rockets on my own, to be honest. I'm really working on more on robots and making things do their task on their own. So yeah, like very rocket specific questions, I'm not sure if I can answer, to be honest.
Okay. Was there a question in Paris?
Yeah. Yes.
Great.
How do you make the rovers, and like how do you make them to see and move? And
right. Yeah. Actually, they work very similar to humans. The robot right now on Mars, it has a camera, and actually a camera with two eyes. So it has two cameras, and it sees similar to a human. And then we need algorithms like what our brain does to process the pictures that our eyes see. These kind of mathematical equations we have to implement or put into the robot, but it has eyes to see, and then it has motors to move. So it is similar. It sees something and then it moves. And then it can also be it can also be driven by a human, actually, the robot on Mars. So it's similar to your remote-controlled car. There's someone here on Earth that can drive the rover on Mars, which is pretty awesome.
That is awesome. Cool. How about Waterdown? I see some curious campers in Waterdown. Do you have a question for Dr. Schoellig?
Yeah, we've got one question.
Okay.
Question.
Yep.
How are like the robots made in special ways? How do they get all their
Could you come a little bit closer?
How do they like not lose like battery in the middle of when they're like in space?
The question was how do the robots keep their batteries charged, or how do they not run out of batteries while they're in space?
In space. Yeah, that's a good question, because that's the biggest challenge here on Earth, that the robots at some point run out of fuel and then they either need a new battery or they have to fill up their tanks like a car. In space, they have two things. They have solar cells, so the sun gives them energy, and they have a kind of energy system that is similar to a nuclear power plant. So they have basically a tiny nuclear power plant, and that gives them a lot of energy. But at some point they run out of energy, and then only the sun energy can be used.
Okay. So I'll go to our first question from Twitter, from Brantford. Shout out to Brantford this morning. They want to know, how long did it take to make the first prototype rocket? So how long would it take to make a prototype of a rocket, or say even a rover, if that's what you're more familiar with?
Yeah, so for rocket and the first prototype, I guess usually it's fast iterations. So do a first prototype, learn as much as you can from your mistakes, do a next one, do a next one. So for a rover, it's probably like 1.5 years to do a proper one. And for a rocket, recently there has been more private companies doing rockets, and they have done it in a similar time frame. But usually they take a year, like with all the calculations and so on.
Oh, wow. Yeah. Lots of work there. And I'm sure a large team also works on it together.
Yeah, absolutely. Yeah. It's definitely a team effort. Yeah.
Cool. So let's go back to Ingersoll. Is there another question for Dr. Schoellig in Ingersoll?
How does the Rover repair itself?
Oh, maybe just come a little closer to your mic. We were having trouble hearing you there.
How does the Mars rover repair itself if it breaks down?
So the question was, how does the Mars rover repairs itself if it breaks down? So there are a few things where it has kind of redundancy, which means it has it has, for example, two computers. And if one fails, it can turn on the other one. And for the important sensors, like the camera, or they also have wheel sensors that measure how fast and how often the wheel turns. These kind of sensors are redundant, meaning they have two of them. But for bigger failures, there wouldn't be a possibility to repair. That's why it's such a difficult mission. Because if something serious goes wrong, then there's no hope to save the robot.
Oh, yeah. So I guess it's a pretty, would you say that's one of the biggest challenges right now, or what a lot of people in the field of aerospace studies are working towards is more reliable rovers, or like how are they going to sort of address that problem?
Yeah, one challenge in aerospace for everything we do, I guess, some of our systems are on Earth as well, right? Is reliability and robustness against failures. it is a challenge, and there's no clear, like there are a couple of formal steps that verify reliability, but yes, that's the most difficult thing to do, I think. Not to make it work once, but to make it work always. Yeah.
Yeah. All right. How about water down? You're still with us. Is there another question in water down?
We did post them on Twitter. We had one question.
Oh, okay.
Are there any robots that are self-aware?
Oh, can you repeat? I missed it.
Are there any robots that are self-aware?
Yeah, I mean, robots are to some extent all self-aware. And that is something actually we work more and more on. They are aware if they don't understand the environment, for example. Let's say they see with the cameras and they should drive along a path, and at some point they don't know anymore where to go because the camera system got worse or it suddenly got darker outside. And then they are self-aware that they don't know. And our goal is that they then would ask for help from humans. So basically the robots do the tasks on their own as long as they can. And if they are aware of the fact that they don't know, then they would ask a human. Stop and ask a human. So that is one way, or they are aware of their energy status, like the battery, how full the battery is or how much energy they have left. So in some way they are self-aware, but obviously they are not as sophisticated as in some of the sci-fi movies. But
Yeah.
little things they know about themselves. Yeah.
Maybe sci-fi movies will. That's sort of like what our future holds. Maybe if we keep.
Yeah.
Do you think?
Yeah, I guess. I mean, for some researchers, that's certainly an inspiration. Yeah.
Yeah.
Yeah. But still, these robots are simpler and not as clever as many people think. There's still a long way to go.
Okay, so we're coming to an end for the time of our call today, but I'll just go to one more question from Twitter. Another one from Brantford. Thank you, Brantford. They want to know, how do they make rockets fly? And I guess I would add to that, how would we send a rover up to Mars? Like, how do we get it up there?
I mean, yeah, they have very powerful fuel. And a rover would go on a rocket, basically, to go into space. Yeah, they have a very specific type of fuel that is not comparable to what you use for your cars. And basically, there are mini explosions that bring the rocket into space. And it's challenging because you can only turn them on or off. So there's no, like you have in your car, where you can put the gas pedal continuously faster. But for these explosions, either you turn it on or off. So you always have mini explosions and then turn off and turn on again to guide it. Like, one challenge is to bring it up, straight up into the air, and that it doesn't fall.
Right. So timing the explosions so that it keeps going straight up, you mean, as opposed to like turning things?
Yeah, basically, it is a challenge to keep it upright during this process. It's like balancing a pendulum on your hand, where it's difficult because it's what we call unstable. So you always have to kind of move your hand such that this pen stays upright, and that's the same for the rocket. With the small explosions, you always have to keep it upright so it goes up straight.
All right. Well, thank you for taking the time to answer some of our questions. I'm sure the campers learned a lot, and hopefully they have some ideas that might help them with their own rocket designs and things to think about. So thanks again, Dr. Schoellig, and thanks for all the questions from our camps who joined us live and through Twitter. Thanks, everyone.
Yeah, thanks. Have fun. Explore a lot. Try things. Bye-bye.